All right, friends, Unit 5. Unit 5 is all about differential equations and their applications to mathematical modeling. So in this case, the key words, of course, differential equations and their application to mathematical modeling. We really do go backwards in this unit by taking a look at differential equations. A differential equation is an equation that involves a derivative. So anytime the derivative is a part of the equation you're looking at, that is called a differential equation. So it could be something where the derivative is explicitly stated, or it could be something where the derivative is a part of the equation, but it's not explicitly solved for, nor would it be easy to do so. So both of those are what we call differential equations. We spend our time looking at these. These will come much, much later. And by much, much later, I mean some course in differential equations as undergraduates in some university under some math major. A couple of quickies. Find all functions y satisfying dy dx is cosine x plus 2x. So this is one of those situations where we say, I think I can back up this truck. I'm looking for the thing whose derivative is cosine x plus 2x. Since we know that derivatives add nicely, we just find the thing whose derivative is cosine x and add it to the thing whose derivative is 2x, and then all of them differ by at most a constant. All of them are different by at most a constant. So you've got your dy dx. You can back up the truck. It's not hard to do. The second example adds one small layer of complexity. Not very hard to do, because all we have here is an initial condition. We've got the initial condition that at x equals 0, y equals 3. So how does this work? Well, it works the same way that the other one works. We take an antiderivative. What's the antiderivative of 2e to the x? Well, that's 2e to the x. And what's the antiderivative of cosine x sine x? And there's a plus c at the end. Well, how do we find out c? We substitute. 3 is 2e to the 0 minus sine 0 plus c. So c is 1. And we always answer the question. So with a plus c, that's a general antiderivative. When we look at a specific function that goes through a specific point, well, that takes all the infinitely many antiderivatives there could be and pins it down. How we doing? Okay. So here's the thing. If the derivative is explicitly solved for, and there's only x's in the problem, then these things are really easy. We crank them out, no big deal. But what if the derivative is not so easy? What if, let's see. What if it looks like that? What if the derivative is x minus y? That's a much more difficult problem. And so what I'd like to do is I'd like to generate for us something called a slope field. And all a slope field is a whole bunch of pieces of tangent line that give us a sense of what solution curves might look like. That's all it does. And I'm not going to start with that big nasty one. I'm going to start with something that's a little bit easier. I'm going to start with that thing. So let's pretend that dy dx is negative 2x. And let's pretend that I want to draw pieces of tangent line at a variety of locations around the grid. So 1, 2, -1, -2, 1, -1. Oh, heck, maybe we go one higher, up to 2. So how does this work? And more importantly, can I copy this? Oh, I sure hope so. Because I'm going to need it here. Yeah, that's going to work just fine. Pardon me while I am astounded by myself. Yes, I'm by myself. Okay, so back we go. At the point 0, 0, I ask myself, what is the slope of the tangent line? Well, the slope of the tangent line is going to be the value of the derivative. And where x is 0, that slope is going to be 0. And so everywhere x is 0, I'm going to draw a teeny tiny piece of tangent line with a slope of 0. Teeny tiny piece of tangent line, slope of 0. What happens when I get to x equals 1? Well, when I get to x equals 1, the slope of the tangent line is -2. Now, -2 looks like this. So I'm going to do my best to draw a piece of tangent line that looks like that. And I'm going to draw that everywhere x equals 1, because the slope of the tangent line, everywhere x is 1, is -2. Similarly, when x equals -1, the slope is +2. Now, are we actually going to check to make sure that your slope is +2 and not +2.5? Probably not, but still all the same, I want to try to be accurate. When x equals 2, what is the slope of the tangent line? The slope of the tangent line is -2 times 2. That's -4. Now, -4 has that sort of a slope. It's got that sort of a slope, so you're looking at something much more vertical looking. Much more vertical looking. And then because I can, it's got a slope of -4 everywhere x equals 2. And similarly, we're going to flip that around, because the slope when x is -2 is +4. So you get this thing. It's called a slope field. And it helps you picture what these curves look like, because you can well imagine now that the curves that solve dy dx is -2x have to look something like this. They have to look something like this. Have to. Just following the way the curves look, they have to look something like that. And that's completely consistent with what we already know about these functions, because we know that y has to be -x² plus a constant. So we know that we're dealing with parabolas. We're dealing with sad parabolas. And the curves follow the slope lines in such a way that we get pictures look like that. That almost makes sense, sort of, kind of, a little bit. I hope so. I hope so. I'll do a couple more. What if the derivative looks like that? What if the derivative is 1 minus y? Well, if the derivative is 1 minus y, then I'll just start at the origin because it's convenient. What is the slope of the tangent line when y equals 0? Well, that's 1. nice 45-degree angle. And everywhere y equals 0, we're on that kind of a line. Everywhere y equals 0, we're on that kind of a line. What happens when y equals 1? Well, when y equals 1, we've got horizontal lines, horizontal pieces of tangent line. And so that tells me that I've probably got a horizontal asymptote at y equals 1 for whatever this family of curves is. Whatever this family of curves is, they have a horizontal asymptote at y equals 1. And then we could ask what happens at y equals 2. Well, at y equals 2, the slope of the little pieces of tangent line is 1 minus 2. That's negative 1. Yes, I have a job. And then down at the bottom, when y is negative 1, those slopes are 2. So those slopes are 2. That's a little bit steeper. And so we'll clone that, and we'll pop it over everywhere y is negative 1. So we can discern that for lower y values, for y values below negative 1, the derivatives actually get more steep. And so you can almost imagine that the curve has to come up looking like this. Similarly, coming from the top, as y gets larger and larger and larger, dy dx gets more and more and more negative, so you can well imagine coming from here curves that look like that. And sure enough, we can solve that, or we will be able to by unit's end, and we can confirm that those are the kinds of curves that you get dictated by the slope field. Okay, well, one more, maybe two more, depending on our time. So what if that's the case? What kinds of functions will we get? Well, at the origin, the slope is 0. In fact, everywhere on the y equals x line, the slope is 0. And then it's just up to us to go from one point to another and just ask, what is the slope of the tangent line at this particular point? So I'll fill it in from left to right. Negative 2 minus 2 is negative 4. Negative 2 minus 1 is negative 3. Negative 2 minus 0 is negative 2. And negative 2 minus negative 1 is negative 1. Negative 1 minus 2, that's the negative 3 from here. Negative 1 minus 1, that's the negative 2. Negative 1 minus 0, that's this negative 1. And then 0 minus 2 is the negative 2. 0 minus 1 is the negative 1. 0 minus a negative 1, that's 1. And then it fills in exactly the way you imagined that it did. And almost there. Almost there. And 3, 2 minus negative 1 is 3, and that's a little bit more vertical. What in Sam Hill happens for curves like this? Well, we can sort of tell that this red dotted line is what we call a slant asymptote. And we can also tell that on the y equals x line, whatever curve you draw is going to bottom out if we're on the north side of the red dotted line. So you can imagine if I were to pick the curve that's going through 1, 1, it's got to bottom out at 1, 1. So you've got some curve that bottoms out and then heads toward the slant asymptote. And then similarly, we're heading toward a slant asymptote the other way. It's hard to tell how it does that on the south side, so I'd have to plot more points to figure out. If I were making a guess, I would say that it shoots up like so, but I can't confirm that because I only have a few pieces of tangent line to help me out there. So, big picture. If I ask you to draw a slope field, I want you to draw teeny tiny pieces of tangent line on graph paper and use those to ask yourself, what does the family of solution curves look like? If you can do that, you are in great shape. It will help you see things that you could not see before. Okay, so what happens now? Well, our next lesson is all about how to analyze these equations numerically using something called Euler's method. So we'll combine the geometry we see with the geometry we can crunch, and then a little bit of analysis, and the unit's all set. All right, thanks everybody.